Hello everyone, today we are going to talk about trigonometric identities with the help of my partner Valeria Beatriz and I, Carlos Aguilar. Let's start with what is a trigonometric identity. They are equalities involving trigonometric functions and hold for any allowed value of the variable of variables under consideration. That is, for any value that the angles over which the functions are applied could take. There are three different types of identities. The first one is the reciprocal identity. If you have a number like, for example, 8, the reciprocal identity is going to be 1 in 8. The second identity is going to be quotient identities. So in this, if you have a fraction like 4 in 4, the reciprocal is going to be 1. And the third type of identity is Pythagorean identities. Here you can see that we have the hypotenusa and the two cut. Well, let me explain a little bit more about the reciprocal identities. They are constituted by the product of two reciprocal ratios. We have, for example, you know that in the triangle we have sine, cosine, and tangent. So the reciprocal of them, for example, sine is 1 in cosecant. The second is cosine, we have 1 in secant. The third tan, then tan is 1 in cotan. If for example you have the cotan is 1 in tan. The second it will be secant is 1 in cosecant, and the cosecant is 1 in secant. Well, now I'm going to explain you how to get the reciprocal identities. Also, I'm going to teach you how to verify and check that they're correct. First, I'm going to give you a tip or how to get in a way more in an easy way the reciprocal identities. First, we need to put the identities in this order. First is sine, then cosine, then tangent, then is cotangent, secant, and cosecant. With this, with this method, it's going to be so easy learn and check which one is the reciprocal. So let's start with the sine. We are going to draw a line to the sine with the cosecant, the cosine with the secant, and the tangent with the cotangent. And with this method, it's going to be so easy. So if we want to know the secant, the sine, we need to know that first we need to put this one is going to be a fraction, and the reciprocal is going to be cosecant. So we put here cosecant. If we want to know the cosine, it's important that if you have alpha here, also we are going to put alpha over here, there. Cosecant is going to be 1 in secant. The tangent is going to be 1 in cotangent. The cotangent is going to be 1 in tangent, secant, is going to be 1 in cosine, and the last one is going to be cosecant is sine. Well, we have two more, and the other two are tanh is equal to sine in cosine, and the cotangent is going to be the reciprocal, so it's going to cosine in sine. We have two different methods of the tangent and the cotangent. Well, now I'm going to teach you how to verify and check that the reciprocals that we've seen before are correct. Here we have the same table or the same order that we have before, but now we change something. We add these identities. We must know that already that the sine is equal to the opposite leg divided by the hypotenusa. Also, we have that the cosine is the leg, the adjacent leg, divided by the hypotenusa. The tangent is going to be the opposite leg divided by the leg, the adjacent leg. The cotangent is going to be the adjacent leg between the opposite leg, and the secant is going to be the hypotenuse between the adjacent leg, and the last one is going to be cosecant, that is going to be the hypotenuse between the opposite leg. And this is going to help us to prove or check. So now let's start with the first one, sine. Remember that sine is equal to 1 cosecant, so cosecant that we have seen before. And to check this, we are going to put the cosecant right here, and we are going to say that the cosecant is equal to 1, and we are going to put this one here with the hypotenuse and the opposite leg. Also, we are going to add a number 1 right here to can make the operation. So now we are going to use the mathematics to resolve this, and we have that 1 by the opposite leg is going to be the opposite leg, and 1 by the hypotenuse is going to be the hypotenuse. And here we can check that this one is also this one, and we already verify the secant. Now for the cosine, we are going to do the same. We have that the cosine is 1 secant, and we know that this is equal to 1 divided by h between the adjacent leg. We are going to add this 1 right here to make the operation, and we know that 1 plus the adjacent leg is the adjacent leg, and we have also that 1 plus h is going to be the hypotenuse, and we can check, and is the same that right here, so we verify the cosine. Now for the tangent, we know that the tangent is equal to the cotangent. Well, here we can check that we can make the comparison with this reciprocal, but also we need to remember that this one is equal to sine between cosine, and now we know that these ones are equal to sine is equal to opposite leg between hypotenuse, and the cosine is the adjacent leg between the hypotenuse. So now we are going to make the multiplication. We have the opposite leg plus the multiplied by the hypotenuse. We can multiply this one, so we are going to put right here, and also we have the hypotenuse by the adjacent leg. Now we are going to delete these ones, and we have that this is equal to the opposite leg between the adjacent leg, and is the same that right here. Now for the cotangent is going to be the same. Remember, cotangent is equal to the tangent, the 1 divided tangent, and we know that we can make the comparison with this, so we are going to use the other equality, that is cosine divided by sine, and this is going to be cosine is going to be the adjacent leg between the hypotenuse and the opposite leg between the hypotenuse. We make the sum. I'm going to make right here. That is going to be the adjacent leg plus the hypotenuse and the opposite leg by the hypotenuse. So now we delete these ones, and we have that the result is the adjacent leg between the opposite leg, and we can check right here that is the same, so we are already verified the cotangent. Now for the second is going to be equal to the 1 divided cosine, that this is equal to 1 divided adjacent leg between h. We add 1 here to make the operations, and we have here that 1 by the adjacent leg is the adjacent leg, and y by the hypotenuse is the hypotenuse. So we have right here the result, and we can check and verify that is the same. And the last one, the cosecant, is going to be equal to 1 divided secant, and that is going to be equal to 1 divide the opposite leg between the hypotenuse. We add the 1 right here, and we know that multiply the opposite leg by 1 is opposite leg, and the 1 by the hypotenuse is going to be the hypotenuse. So we can check. We have the opposite leg between the hypotenuse, and we have the same right here.
There are two trigonometric quotient identities, tangent and cotangent, and they have the property of relate by means of a quotient, the trigonometric functions sin and cosine. Here we have that the tangent of the angle is equal to the sin between the cosine, while the cotangent of the angle is equal to the cosine between the sin. Now, as trigonometric identities are related to the trigonometric functions, we're going to be using them for demonstrate the quotient identities. This is another method that we're going to be using right now. First, we're going to start writing all of them. First, the sin is going to be equal to the opposite leg that we're going to put like in Spanish, like en cateto opuesto, divided by the hypotenuse. Now the cosine is going to be equal to the adjacent leg, like in Spanish, cateto adyacente, divided by the hypotenuse. The tangent is going to be equal to the opposite leg divided by the adjacent leg. The cotangent is equal to the adjacent leg divided by the opposite leg. The second is equal to the hypotenuse divided by the adjacent leg, and the cosecant is equal to the hypotenuse divided by the opposite leg. We're gonna be using this for demonstrate the quotient identities. So if we have that the tangent of the angle is equal to the sin divided by the cosine, we can demonstrate it putting this in terms of the trigonometric functions. For example, we can say that the tangent is equal to the opposite leg divided by the hypotenuse, and all these divided by the adjacent leg divided also for the hypotenuse. Now we're going to be canceling this, and we can say that the tangent is equal to the opposite leg divided by the adjacent leg. And if we go to our functions, we can say that this is equal to the tangent. Here we have it. So we're gonna put that tangent of the angle is equal to tangent of the angle, and we have demonstrated the first identity. We could cancel the hypotenuse because it was the same in both, but if it wasn't, we could use the sandwich law that we could demonstrate here, and we can say that the tangent of the angle is equal to the opposite leg divided by the hypotenuse. All these divided by the adjacent leg divided by the hypotenuse. And for sandwich law, we say that it is the opposite leg multiplied by the hypotenuse divided for the hypotenuse equal, and this multiplied for the adjacent leg. We cancel hypotenuse with hypotenuse, and we have the same result. And this is the opposite leg divided by the adjacent leg. That is the same, but in here we just cancel the hypotenuse because we know that if it's the same, we can cancel it. But if these weren't the same, we could just use the sandwich law for see if this is true or if it's false. In this case, we have demonstrated again that this is this is true and it's equal to this identity. Now we're going to do exactly the same but with the cotangent. We have that the cotangent is equal to the cosine of the angle divided by the sine of the angle. We can put this again in terms of the functions, and we say that the cosine is equal to the adjacent leg divided by the hypotenuse, and the sine is equal to the cosine the opposite leg divided by the hypotenuse. Just as we say, we can use the sandwich law, and we could do the whole process, but we know that if we have hypotenuse under both of them, we can just cancel it, and we have that the cotangent is equal to the adjacent leg divided by the opposite leg. If we go to our trigonometric functions, we have that this is true because the cotangent is equal to the adjacent leg divided by the opposite leg. So we have demonstrated this identity, and this is the last quotient identity, and we now have that this is true. The Pythagorean trigonometric identities are obtained by applying the Pythagorean theorem to the definition of trigonometric functions. There are three identities, and they are fulfilled for any value of angle x. They are the square of the sine of the angle plus the square of the cosine of the angle is equal to 1. The tangent to the square of the angle plus 1 is equal to the secant to the square of the angle, and 1 plus the square of the cotangent of the angle is equal to the cosecant to the square of the angle. The unit circle is used in mathematics to relate to the basic trigonometric functions in an easier way. It's very useful when we want to easily demonstrate the Pythagorean identities. Since the radius of the unit circle is 1, this makes it easy to apply the Pythagorean theorem and results in x coordinates being cosine and y coordinates being the sine. So for start this, let's demonstrate the Pythagorean identities. We're gonna start with the first, that is that the square of the sine of the angle plus the square of the cosine of the angle is going to be equal to 1. And now we're going to help us with the tool that we already mentioned, that is the unitary circle. We're gonna draw a circle, and we're gonna put the Cartesian plane, and we can draw an angle. For example, we can say that this is the angle x. We're gonna put a point in the circumference, and we can say that this point could be P, and it's going to be x and y. For this, we can say that the cosine of the angle is going to be equal to x, and the sine of the same angle is going to be equal to y. And now we're gonna use the equation for the circumference, and as the radius of the circumference is equal to 1, we're gonna say that x to the square plus y to the square is going to be equal to 1. And now if we replace the values, given that we know that x is equal to the cosine and y is equal to the sine of the angle, we could say that the cosine of the angle to the square plus the sine of the angle to the square is going to be equal to 1. And now we have demonstrated with the help of the unitary circle the first Pythagorean identity. We can put this point in any place in the circumference and this rule is still going to be valid. Now let's move with the next identity that is going to be given by this one, and for this we're going to be dividing this identity, the sine to the square of the angle and plus the cosine of the angle to the square too, equal to 1. And we're going to be dividing this by the terms of the cosine to the square. So let's put the cosine to the square of the angle under every of these terms. Cos 2. And we're going to remember that the sine divided by the cosine is equal to the tangent, and the 1 divided by the cosine is equal to the secant. We saw these properties in the last identities, so let's use them for proof that this is correct. So the sine of the angle divided by the cosine is going to be equal to the tangent of the angle. Then now we're gonna adding the plus. The cosine divided by the cosine is going to be equal to 1, and 1 divided by the cosine to the square is going to be the secant to the square. So let's put this there. And now we're gonna have the second identity that says that the tangent of the angle to the square is going to be equal to the secant to the square of the angle when we add a 1. Now we just have one identity left, and for that one we're gonna do the same thing that in the one before, but instead of the cosine we're gonna be using the sine. So if we have that the sine of the angle to the square plus the cosine of the angle to the square is equal to 1, we're gonna be dividing this in terms of the sine of the angle to the square. So we're gonna put that in every term of this just as we did before. So we're gonna put this under every term. And now we're gonna be using, as in the same case, some properties. For example, the one that says that the cosine divided by the sine of the angle is equal to the cotangent of the angle, and the 1 divided by the sine of the angle is going to be equal to the cosecant of the angle. So if we put that here, we can say that sine divided by the sine to the square, both of them, is going to be equal to 1, plus the cosine divided by the sine is going to be the cotangent of the angle, and 1 divided by the sine to the square is going to be equal to the cosecant of the angle to the square. And now we have demonstrated the last one, and here we have demonstrated the three of the Pythagorean identities. Let's remember that we use for these ones some other identities. For example, the one that says that the tangent is equal to the sine divided by the cosine, and that the cotangent is equal to the cosine divided by the sine. We saw that in the quotient identities. And for 1 divided by the cosine equal to the second, as 1 divided by the sine equal to the cosecant. And we saw this in the reciprocal identities, and we already demonstrated that once. Well, that was all for today's video. We hope you have understood the topic and that you like it. Bye.